is something that I take a lot of passion in. Measuring soil health, been practicing on a family farm. For at least about 15 years now, even though actually only 5 years ago I started measuring things. And along the way, I've learned a lot of lessons. So I'm going to cover some things very quickly today. I'm very passionate about soil health and being able to measure change, describe change, influence change. Cover crops, I think I planted my first one in 2004 on a family farm. I like this phrase, roots in the ground all year round, this sustainable green bridge. I didn't coin those phrases, but, having active roots in the ground more months of the year, that has a huge impact on the biology of soil, productivity of the soil in many ways. Some of the, benefits of cover crops, when I first started this in 2006, we got some cost share. I think that was actually 2004. We planted some rye after soybeans, looked at it very simply, soil conservation, weed suppression, better seed beds. And along the way, we sort of morphed to what I consider level 2, building organic matter, nitrogen scavenging, improving soil health. And then lastly, level 3, I began to realize some of the more advanced benefits with soil health, root exudates, releasing organic acids and growth regulator compounds. This whole concept of releasing carbon dioxide into the crop canopy, improving soil health and soil microbial activity. And lastly, I've only realized, and what I consider level 4, that an optimal soil health, that soil system so well buffers the soil that it reduces inherent soil and yield variability that many farmers deal with on a year-to-year basis. These are benefits of cover crops. We're talking about soil health and measuring those effects on the soil community, these community of microbes, the diverse combination of fungi, bacteria, protozoa, insect, fauna, and worms. This is a community that's pretty adapted and entrenched. It's hard to shift species in a short time, like on a year-to-year basis, but this community is quite easy to stimulate and improve that community and what they do in the soil. Do covers impact the microbiome? Not a lot of research has been done on this. I came across a couple of papers. There's one I have posted up here from the Journal of Soil and Water Science. Covers promote fungi and have in a higher fungal ratio. You have greater carbon mineralization, also known as soil respiration. Soil microbial activity was positively correlated with both the size and the composition. That fungal to bacterial ratio, that greater that ratio of fungi to bacteria in the soil, the greater the microbial activity. And I have a case on our family farm where we have very polar fields that illustrate that point. Arbusular mycorrhizae were more abundant under, cereal systems, monocot systems, oats and cereal rye. Other more traditional fungi were more positively associated with hairy vetch and red clover. And in weed communities were more associated with Actinomyces and gram-positive bacteria. Not a lot of research on how the covers are affecting the microbiome directly, some DNA research going on, but looking at some of these today's conventional soil health metrics haven't really been applied to this type of a study, and that's very high on my mind right now. How do the covers impact the microbiome's engine? I sometimes think of the soil as an engine. You have all these little microbes in there. They're all churning along, doing their thing. I think, paying attention to soil health means learning to farm the soil as a crop, and something that farmers don't do. They farm the crop, not the soil. That community can be stimulated to process more carbon, mineralize more nutrients, stabilize soil aggregates. That's very measurable. And these metrics can measure your soil's biological output. And getting people to think in this concept of a soil engine, or like measuring your blood pressure or your pulse, measuring these things, you begin to understand the soil's ability to produce. We can't have soil health without soil quality. That's kind of an old term that dates back to the 1990s. The microbes and fauna, they all live in the soil. That's their house. And if the house isn't right, doesn't have the right structure, the pH, salt, salinity, if there's not a lot of feedstock there, you can't have good soil health. Even if you've got lots of microbes, if the house isn't right, you can't have good soil health. So you have to really understand and investigate a little bit the chemical, physical, and biological processes in that soil. And if your chemical and physical processes aren't in their sweet spot, it's hard to have good biological activity. I never want to take away from how important the visual assessment is. Never discount the spade. Comparing a tilled soil to a no-till soil with covers, going out there with a spade, and just how easy can you push that spade into the soil? How crumbly is it? What does it smell like? You can never understate and emphasize enough that this visual assessment is important, because it really tells us a lot. You don't always have to have a meter and a chemical to measure these things. Visual assessment still works pretty well. You're probably familiar with that Canadian soil Undies test, where you can bury a pair of your Undies in the soil and you can see what happens. Obviously, a more biologically active soil is going to cause more decomposition of that cotton fabric, and it's a very visual example of how healthy and biologically active the soil is. Moving on, and in this biological activity, there's a series of measurements one can apply. Some of these are quite simply, some of these are very simple. Some you can do yourself. Some you can send out to commercial labs. Soil respiration, which some people refer to carbon mineralization, at 24-hour CO2 level. There's a burst test. There's a basal field test. The Solvita test that you see on your right there is an easy-to-use technology that measures that. Nitrogen mineralization, there are two measures out there, SLAN and ISNT. The soil health test that was developed by Rick Caney, and the soil health score. That's PLFA test and DNA sequencing that look at microbial biomass, describes the landscape. Of course, the Cornell soil health test, and then the Soil Health Institute is developing or describing some additional tiered metrics that could describe soil health. But I think what's important to remember about some of these tests is what can be done in a commercial lab versus what can be done in a research lab. So the tests that will float to the surface are those that can be done maybe by yourself or by some of the commercial labs that choose to get involved in soil health testing. One of the outcomes of good soil health is water stable aggregates. On the left, that we've all seen that visual slate test. You take a well-structured, stable soil versus one that's degraded, and you drop them in a beaker of water, and you see what happens. There's another test at our Woods End lab called BAST. Quite simple little test that you can actually measure the volumetric water stable aggregates. This is one of the outcomes of soil health. But not always, and I'll come back to that. You can have great soil health and not necessarily always be able to water stable aggregates. Sometimes I think that's a big unknown. The soil health test that has become pretty popular can be done in a commercial laboratory. The NRCS's Conservation Security Program has been funding a lot of soil testing of that Haney test, again known as the soil health test. It looks at the soil respiration to estimate microbial activity. It measures microbial active carbon, nitrogen and phosphorus, mineralization, and how much potassium is coming out of that inorganic and organic system. And at the end of the day, it calculates the soil health score. Based on some of these factors, respiration, carbon, nitrogen ratio, it gives you a score how well your soil is, like on a scale from 0 to 40. Then in the soil health test, I'm not going to spend much time, but it looks at all these different components: nitrogen, phosphorus, and potassium, both what's in the soil solution, what's coming off the exchange capacity, and what's coming out of the organic matter. And it looks at all three components, and it essentially does a budget and sums those up. And the soil health test kind of estimates how much NP and K will come out of that system in any given year, providing the weather cooperates and the microbes are working. So it does give you some kind of potential budget as well as a soil health score. Another test I should qualify them. These tests, I've done them all many, many times. And I have some examples here I'll show in a minute. PLFA test, phospholipid fatty acid test, kind of a complicated test that has some value. All your microbial groups like bacteria, fungi, they have a specific fatty acid profile signature that you can measure. And it becomes very useful kind of for characterizing your community in the soil. As you can see, it separates out bacteria. It separates out the fungi a little bit and also lists out protozoa. It can generate a lot of data and ratios, but is often hard to interpret and difficult to shift. It can be done in a commercial laboratory. This test works really, really well when you're describing soils with different histories and landscapes. I don't find it very effective if you're applying a product or a treatment in a short term. It's very hard to see a change in the community. But describing a forest soil, a timber soil versus a permanent crop soil versus an annual crop soil versus maybe different landscape changes, this is a very effective test for describing that community. So some of the soil health metrics, I just want to kind of summarize. They measure the results of increased microbial activity. In this carbon mineralization, this respiration is very, very sensitive to change in community activity. It identifies the amount of active carbon in a key feedstock. And we can't say enough about this importance of this short chain carbon molecules coming out of manures, what's leaking out of roots. And this feedstock is the key to really driving microbial activity. It focuses on carbon and nitrogen mineralization and flow through the system. And, it's very sensitive to, biological product applications, planting covers, and adopting no-till. So I've always been quite amazed that these simple metrics, like the Haney test, some of the Solvita tests, the Cornell test, they are very, very effective in the short term. If you're stimulating the community in that soil, you can pick that up. It's very, very sensitive. As I said, with the PLFA metric describes microbial landscape in the soil. It best describes things in a historic basis. But one thing it calculates is total microbial biomass, which correlates very, very well with the soil health test. Obviously, the greater the microbial biomass correlates with more microbial activity. And some people still hold a kind of a dim view of the value of this test relative to the cost. As to what you can actually learn from it when you're trying to manage fields on a day-to-day basis. The Cornell Soil Health Test, or Soil Health Assessment, an interesting test, tells you many of the things that the Haney test and the Solvita test combined already tell you. They look at their own selection of things, looking at some of the chemistry, soil texture, this active carbon, this what they call PLC or permanganate oxidizable carbon. I would never emphasize enough how important it is to know how much of this is in your soil, because this is the little feedstock that's driving those microbes to work. Respiration, aggregate stability. So this is another test, not a test that will be adopted by a commercial lab because it's sort of a cumbersome and lengthy to do. But it's pretty well known out in the Northeast. But after doing a lot of these tests and investing a small amount of money and evaluating all these metrics on various soils and the various management systems, I've sort of arrived at what I like my top 5 tracking tests in the soil. Organic matter, just by loss by ignition, something very simple any commercial lab can do. I mean, if you don't have good organic matter levels, you're never going to have good biological activity. You think of California soils with less than 1%, in the Central Valley, less than 1% organic matter. You think of the prairie soils now between 3 and 4% organic matter. Organic matter is a great metric. You just have to know where that's at. And if it's lacking, it's pretty hard to have good soil health. Soil respiration, that's that measure that aggregates everything together that's going on in the soil. A lot of things affecting that community out there below the soil surface, and carbon or soil respiration really measures that outcome of that. Nitrogen mineralization, very important because that's an outcome of good activity, good respiration. But you can have good respiration and poor nitrogen mineralization at the same time because it relates to the quality of your organic matter. Aggregate stability, great outcome. I think that's what we all want, a very stable soil that can resist the ravages of nature going on in this active carbon. I like those 5 things. I can measure these 5 things. That tells me a lot about the soils and how soil health is tracking. I'm just going to go through an example here of some fields that I've tracked, that I've measured very extensively, developed a baseline, follow some trends. These are all related to our family farm in Nebraska, and they have a range of soil health. A cool season mixed pasture, very excellent health. You can never emphasize there's something special about livestock trafficking and their waste deposition in the field. One field, number 2, called buds, very, very excellent health, good health, because I apply my own recipe for soil health, which includes no-till, some gypsum compost, some annual covers. Alfalfa is a great field because alfalfa is a permanent crop. You can have really great, really good soil health. A switchgrass, CRP, switchgrass since 1985. No inputs, no livestock trafficking. You would think that a permanent grass system like that would have good soil health, but without any inputs or anything, it's only minimal. Then with the 5 and 6 are 2 fields that one has 5 very, what I consider mediocre health, and number 6 is very, very poor health. And the data I have from these metrics will show that. One thing about number 6, the land isn't owned by the family. It's been in the family for decades, but it's got poor structure and it doesn't have that earthy smell. Since we don't own the land, we're limited to what we can do with that, but it's very characteristic of a soil that's got poor health. You were to go out and dig that up, and with a spade, it doesn't have good tilth. It doesn't have the good odor that we're so used to expecting from a healthy soil. So I just want to look at a few things here, some data. You'll see a bunch of tables like this where I have these tables, these graphs where I go from the worst field called Joy's to Davidson's to the CRP to alfalfa to buds to pasture. These follow this kind of gradient, this curve here from poor to good. Looking at the soil organic matter carbon here, that's just percent here versus active carbon here on the parts per million. As you can see very, very clearly, as organic matter goes up, so does your active carbon. There are 2 measures of active carbon. In the orange graph, this is that permanganate carbon done by our Cornell soil health test, and the gray line is the water extractable organic carbon from a carbon analyzer. But they follow the same trends. As organic matter goes up, so does your active carbon. So that's a very important thing, and the better the soil, generally you're going to have higher pool of active carbon. The carbon to nitrogen ratio, sometimes we think of carbon to nitrogen on total organic matter. We think of things like wheat straw might have an 80 to 1 Maybe we get down to soybean stubble, that might be 25 to 1. I'm not talking about that total carbon to nitrogen. We're talking about the water-soluble carbon to nitrogen ratio. You see that as organic matter goes up, you don't necessarily see the same trend in this water-soluble carbon to nitrogen ratio. And you see that on these better fields, this ratio is much lower than on the poorer fields. And on the CRP, it's like 35. It's like 35, the ratio 35 to 1. So quality of organic matter, of this organic matter, really is important. The lower this carbon to nitrogen ratio in this area of 10 to 1 or less, this is according to Rick Haney, the greater your microbial activity and the healthier the soil. When you get to something like CRP, where you have a lot of thatch, a lot of root mass, no inputs, no nitrogen or anything, you can see what happens here. This carbon to nitrogen ratio really goes down. Well, this ratio really rises as you get more carbon in that system, and the health of that soil, at least from recycling and microbial activity, is not going to be as high because the quality of the organic matter is very low. Aggregate stability, using that Cornell's test, which is in the orange, and the blue, which is Woods End's test, you'll see that, again, versus organic matter, aggregate stability tends to increase. I found this very interesting. This test, these were composite soil samples taken from this field and sent off to the labs. I found this one is 13.7% water stable aggregates, very low, based on the Cornell soil health test. So what I did, I really wanted to, this aggregate stability, it ranges from values from 0 to 80%. The higher value is being rare. That's the percent of water stable aggregates in the soil. You tend to lot numbers someplace here in the greater than 30%. You start to get up in some permanent crops like alfalfa, you can get greater than 60. But what you want is aggregates that don't break down. They're very water stable. So the higher proportion you have water stable aggregates, the more stable that soil is, that profile is in general. But in this one field of buds, I decided to grid soil sample that. So I had 28 points in an 80-acre field. And you can see this scatter of points across there from 28 points. And if you notice that the midpoint of this thing is probably around 18% water stable aggregates, right? Something very, very low. And Woods End Lab did this, and then I redid it myself, ran this test myself, and sure enough, these samples were low. And you can see in this little test, these aggregates in water, they just fall apart. So after 15 years of no-till covers, compost, other practices, the soil is lacking aggregate stability, right? I begin to wonder if I'm lacking mycorrhizal or glomalin or lacking, but something's not quite working in that system, even though we practice good soil health. So I began to think about this. Can excellent soil health and conservation practices, which we, on this field, they serve as a pretty good surrogate for weak aggregate stability. And so you can have good soil health and not necessarily foster great aggregate stability. I still consider this a great unknown. Nobody's measuring aggregate stability on the fields. I think if they started doing that on any kind of general basis, they would probably be surprised. This might not be as stable as they think. And I'm not quite sure what the answer or the solutions are, but I believe we need more work and understanding of how to promote better aggregate stability. And in this field, we plant ryegrass every fall. So that's part of the rotation, but yet we're not really building aggregate stability. Don't have the answer to that yet. Arbusular mycorrhizal levels, I looked at that, remember that mycorrhizal and that byproduct they produce, glomalin, is one of the glues that hold together soil particles and build soil aggregate stability. Very, very hard to measure mycorrhiza accurately in the field. There's no simple way. When you look across the spectrum of the fields, like down here at the bottom, using the PLFA method, they measure this. The Davidson farm and Joy's very, very poor fields had very little mycorrhiza. This is a very poorly structured soil. When you get up here, buds was probably pretty low as well. When you get up here to something like the pasture and the CRP, the percent of total microbial biomass, that mycorrhiza was very high. I would expect that in a pasture. In this grass system with no inputs of any sort, was also very high. So there is a relationship between mycorrhiza levels and the quality of your soil. One of the very common popular tests today most people have heard of is that Solvita test. An excellent indicator of microbial activity, easy to do, aggregates together all the factors that influence respiration, influence the microbes. If you look at this, this is a image that Dr. Britton sent me from Finland. You look at what happens when you these little paddles, when you pull them out of a packet, they're blue. And over a 24-hour period, depending on how much respiration is going on in that soil, you turn colors from blue to various shades of orange and yellow. And the more yellow the paddle, the higher the respiration. So as an example, in here's a cover crop mix, 6-way, good growth on top of a tiling line, very, very high, very, very high respiration. But in the same mix in bad growth conditions, between tiling lines where there's no drainage, there was not very much respiration. The point being that while they both had cover crops, the house here wasn't right. Not good aeration, and so the respiration in that soil was poor. This is what happens in respiration. The conditions of that soil, pH, organic matter levels, porosity, aeration, moisture content, temperature, all drive microbial activity and the outcome and the respiration outcome. Basal respiration trends, I think, are really important. You can measure respiration in the cover crops. You can see this. You plant a cover crop and you go in there and you can measure this effects on cover crops versus respiration. I've done it many times. If you look at a soil that has nothing growing, a fallow soil, your parts per million of respiration coming out of that soil will be 10 or 20 parts per million. You have a very vibrant, active cover crop. Your respiration rates can be 100, 120, 180 parts per million. The greater the biomass, the more diversity going on in that soil, both in plant species and microbes. That number, that respiration value can really shoot up. But what's interesting when you look at the basal respiration trends, and you think about managing and farming your soil, you want that soil to be biologically active through the growing season as long as possible. If you look at basal, which is field testing for respiration, you'll find that, and this is just data I generated myself on the farm, you see that this respiration rates will they increase till June as the soil is warming up, becoming more active. These respiration rates they go up, but then they tail off. They tail off for several reasons, because of increases in temperature, maybe moisture, but largely because you don't have enough active carbon in that profile now to really keep the microbes well fed and active. The theory would be that if you could drive this active carbon level, you can maintain this basal respiration trend through the season. And maintaining that engine, recycling those nutrients, that will go about, makes the soil more productive and the crop more productive. So planting covers here can really play a big role, because you plant your covers. We're just about done here. You plant your covers and you can stockpile some of this active carbon. when you stockpile this active carbon, you can maintain this level of basal respiration. There's also nitrogen mineralization. There's the ISLANI test, the SLAN test. You look at things like a multi-species cover crop, 155 parts per million of ammonia liberated that's released. So you can measure nitrogen mineralization. I think that's very important when you're adding organic matter like cover crops to a system. You can estimate how much nitrogen can come out of that system. And that's another test that's available. We looked at Solvita versus SLAN, and I've already mentioned across these fields that respiration goes up as the field health gets better. But if you track SLAN, the nitrogen mineralization, like here, it goes down because organic matter quality matters, as I said earlier. So if you just use respiration as a metric and estimate nitrogen mineralization, it might not be quite accurate. So quality of organic matter matters in that system. And then lastly, you look at these soil health scores. That comes out of the Haney test. And you look, and I ran this across these fields, across 3 different labs, and you'll see that they all, while the numbers aren't quite the same, they all follow the same system from the best field down to the worst fields. For the whole soil health score, you want numbers someplace up here greater than 20. And 18 to 20 or greater is where you want to be with the soil health score. The Cornell soil health measure of soil quality pretty much tracks the Haney test. As you can see across these 5 fields, it pretty well tracks, even though the scale's a bit different. The microbial community, and I looked at the PLFA test. Again, if you look at across the 5 fields from the best, from the worst to the best, the total microbial biomass and the soil health ranking, they were perfectly correlated, is that microbial biomass relates directly to soil health. The fungal to bacterial ratio, just wrapping up here, we have a poor field, weak earthy odor. Soils are more bacterial dominated. As I go up and you look at this ratio, as I get to the good fields here, very biologically active, the soils are more fungal dominated and the strong earthy odor. So that fungal to bacterial ratio, as I said in the beginning, makes a difference. In my last slide here, soil health metrics, they work. They're very descriptive. They are sensitive to change. And, seems that we need some work done on different covers and combinations in a scientific study, really applying these tools to see how different species and combinations really affect that soil engine.